Hello, and welcome to the Logistics Officer Association On-Demand Training course. This is Simon Bezrukov with KPMG LLP, and I'm excited to spend this time together to talk with you about simulation and digital twin. Here at KPMG, I'm a director with our Lighthouse Innovation practice and lead for the simulation service offering. Now, as a computer scientist and operations researcher by trade, it's been my personal privilege to support our defense and commercial clients on this very front for the past 16 years. And in the next half an hour, we plan on sharing with you some of the new and exciting ideas in the space, introducing you to a couple of high-profile use cases, and providing some structure to help you think through and identify instances where those techniques can be applied to solve some of the biggest challenges that our clients and industry are facing today. Now, to make things even more concrete, we also have a quick demonstration for you of a decision support capability that we developed to study the COVID-19 industrial manufacturing supply chain impacts. After all, it's exactly this ability to predict the unknown and experiment along the way that makes simulation and digital twin such a unique concept. First, let's take a quick look at the topics for today. We're going to start with a couple of definitions, since I'm sure that many of you have already heard of simulation and digital twin, since these concepts are becoming very popular in our community. But the one thing that you'll find is that there are a number of alternate definitions, and I think it'll be critical for us to normalize on these. Although our list certainly won't be exhaustive, we will also work to cover some of these more common methodologies for both the fields in the later sections. Next, to make things more concrete, we'll look at a specific example of how we've helped one of our clients. Please keep in mind that data in all of today's use cases has been completely de-identified to protect their identity, because, of course, we take client confidentiality very seriously. After this first example, it's back to theory. We'll dive into the why and how, and then jump to our second example, an industrial manufacturing client. We'll take a look at their core business challenge, the specific modeling approach that our team came up with, and then even take a glance at the solution, a decision support tool that we built to help them run course of action analytics. With that, let's get started. Our first key definition is simulation. We describe it as a set of techniques and a platform which allows us to build an approximation or a model of reality. This notion of a model versus the real thing is very important, and a subject that we're going to come back to multiple times during this course, largely because it is the main challenge and essential theme that you're going to face in building simulations and digital twins. The question of how real does it need to be? Let me ask you a question. What is the difference between the three pictures on the top right? None of them are actually Lisa Gherardini, the subject of Da Vinci's arguably most famous piece, known for the Mona Lisa smile. Even the real painting itself is an abstraction of the real thing. And then as we move left to right, we can consider the artistic impression in the middle, followed, of course, by the smiley icon. So in the end, if our real objective was to simply convey a smile, do we really need to paint a Mona Lisa? Well, when it comes to simulations, this concept of scale of abstraction is critical. While we want our models to allow us to be as accurate as possible, we always sacrifice and make programmatic trade-offs between complexity and compute time. After all, the best model for reality is just that. It's all the atoms that make up here and now. Anything else is going to be an approximation, but given the appropriate framing, a simple but usable model may just be enough to give us a useful result. One of the more well-known methodologies that we follow is known as the Sargent circle, pictured on the bottom right. We start on top by quantifying through analysis the key drivers of behavior. For instance, Let's say that you wanted to build a simulation of a new product marketing campaign, which would allow your clients to optimally allocate funds to different kinds of advertising mediums. Well, first, try and understand the current market and customer. To that end, you might get statistics and run some regressions that would allow you to gauge the preferences of those prospective populations, how they consume that information, and narrow down the number of available options. Let's say it's Facebook ads versus Google ads versus direct mail. Then you would put together a conceptual model of how your proposed marketing channel affects each of the subpopulations and then package it as a computer model. During this development, you are going to be going through frequent verification steps and boundary testing in order to make sure that the mathematical conceptual model was coded accurately. Now that you have a computer model, you can start running your simulations and try any number of different strategies, maybe even all of them, to see what effect they have on the main outcome variable. Let's say that's purchases of that new product. Now, importantly, these can be validated against what we see in the real world, typically by doing small test trials. So when a simulation proposes a particularly successful and perhaps even counterintuitive strategy, oftentimes the best way to prove it, or fail fast, which by the way is okay, is to run a small real-world experiment. This is a key concept in our takeaway. Once built, simulations allow us to carry out a number of experiments and provide a way to safely try what we might not be able to readily test in the real world. And if something doesn't work, we simply reset and try again. Now, let's define digital twins. Simply put, a digital twin is a replica of a real-world object inside a simulation. By following the same series of steps that we did with the simulation, which represents the overall digital world that those objects inhabit, we can come up with a virtual representation. Digital twins come in a number of variants. Traditionally, we draw a distinction between an entity and a process. While both exist in the real world, one is more tangible than the other. An entity is a physical object, like an airplane, a person, or a building. A process is more of a logical construct. For example, a series of steps that your current application goes through before a loan officer makes the final decision. In just a bit, we'll jump into a real-world use case for each of them in order to demonstrate how digital twins can be built and what value they bring to their designers. Now, as you might imagine, having a virtual copy in a simulation does allow us to perform all sorts of experiments. A great example is diagnostics. Let's say that we have a digital twin of an aircraft where we store all of the flight telemetry and conduct real-time analysis on vibration data in order to preemptively diagnose issues before they occur. But even more broadly, they allow us to plan for the uncertainty of the future, because by changing rules of the simulation, we can see how the digital twin responds. Let's start with a process example. In this use case, we'll talk through how a financial services institution created a digital twin of their loan approval process in order to anticipate and solve a problem in simulation. This particular client was concerned about their ability to make timely decisions on loan approvals, given the potential seasonal influx of new cases and a fixed number of staff. Looking at the diagram on the right, you can see how we digitize their process by breaking down the sequence of the work into discrete steps and then resource loading them inside the simulation based on the number and type of the staff that were working in each phase of the process. For example, in step A, they had 4 employees. In step B, they had 10. And then step C1 was completely automated. Next, we calculated some baseline statistics for the loans themselves, since the amount of work that needed to be done in order to advance each application from one step to another differed by application type. Finally, in order to prove that the model was calibrated correctly, we ran a volume of applications which was consistent with their status quo operation through the model and compared key utilization metrics against their historic baseline in order to make sure that the outcomes were consistent with reality. Now that we've had a proven model, we begin our stress tests. What would happen when we increase the volume from the baseline of 500 new applications per week to 700? In Figure C, looking at the utilization measures, we can see that the current process could not handle the additional volume, since the utilization within step F2 is consistently at 100%. In building these tools, there are typically established set of benchmarks for the maximum, and if this number even starts approaching 100%, we know that this step is likely bottlenecking the overall throughput. Now, the beauty of a simulation is that it's not only capable of identifying the problem, but can be used to evaluate strategies for solving it. In this case, the system recommended a very small change. If you look at Figure D, it appears that by moving 2 staff from step C2 to F2, assuming of course that these folks were cross-trained and had the right skills to work in both areas, we were able to balance the system and reduce the utilization of the staff in step F2 to a much more manageable 70%. This is just one example for how having a digital twin has allowed one of our clients to prepare for the unexpected ahead of time. Now, we'd like to get back into a bit more theory before our case study and demo in order to discuss some of the core benefits of simulation. In particular, it is interesting to examine the parallels and differences between it and traditional data science. We view these disciplines as two sides of the same coin and largely complementary. Data science, and I specifically mean machine learning, excels in an environment where we have both a large amount of samples and the data itself is more or less consistent. Simulation, however, is useful for exploring problem sets where that is not the case. By its very nature, it is constructive and does not rely on vast quantities of data. Instead, a framework of rules that probabilistically connect cause and effect. And so traditionally, simulation has been the tool of choice in building models that embrace this notion of a cone of uncertainty. A great example is traffic. Let's say that you are driving on a highway. Well, the next few seconds are going to be driven mainly by physics, right? Your car has mass and a velocity. But what happens if somebody else swerves into your lane? It is in cases where actions of a single actor have disproportionately large global effect that simulations really shine. They also function well when there's no baseline whatsoever, or the system behavior is changed by a large exogenous shock. For example, COVID-19 and its impact on global supply chains. This has never happened before, and many of our legacy analytic techniques struggle with these kinds of problems. The key takeaway here is that simulations offer us a unique answer to a question of what could happen. In order to build simulations and digital twins, we rely on 4 key modeling disciplines. They are discrete event, agent-based, system dynamics, and Monte Carlo. In a discrete event model, time is not linear. Instead, it jumps between milestone events inside the simulation. These are usually points in time at which the overall system undergoes a change. Their immediate application are supply chains, distribution logistics, industrial production, and workflow systems. And in our experience, they are the most common type of simulation. In an agent-based model, the system behavior manifests itself out of the individual interactions of the agents, each with their own sets of goals and means. As such, these are best used to characterize any system where emergence is a key characteristic. For instance, modeling a crowd of pedestrians or the flow of traffic. On the other hand, system dynamics represents the world as a series of stocks and flows. This technique excels at representing complex, nonlinear behaviors where a series of seemingly small changes can suddenly eclipse a threshold and trigger a large shift in an outcome. They are best suited for economic stability and disease modeling applications. And then finally, we have Monte Carlo. This set of techniques allows for probabilistic characterization of behavior and are most often used in combination with the other three in order to test parameter space and model stability. The key takeaway here is that each discipline in reality represents a different field of mathematics and can constitute an alternative, viable way to build a simulation. But in practice, best results are usually achieved by hybridizing those techniques within the same model. Now, let's take a look at our second real-world use case. In addition to looking at this business problem and the respective solution, we wanted to share with you a quick demonstration of a decision support tool that our analysts built. Since the ability to engage with the digital twin in an interactive fashion is really one of the main value propositions of a simulation. But before we jump into that, we want to spend just a little bit of time on the underlying methodology, since this is quite a bit different than the previous process modeling exercise. Now, this industrial manufacturing client was building a physical asset, in this case, an aircraft. They were concerned about the potential impact and interruption that the COVID pandemic would have on their ability to deliver these platforms on schedule. We adopted an industry-standard methodology that looks at the production flow in terms of availability of three key resources: parts, people, and facility space. Each of these three can be thought of as requirements at every step of the assembly process. If any one is missing, then the work cannot be completed and move on to the next step of the line. Let's first take a look at parts. Now, as you might imagine, the individual components required fall into different categories. Some in this red bucket are more scarce. This could mean that they're large and expensive. A good example would be an aircraft engine. And maybe for those reasons, we don't maintain a large safety stock buffer. On the other hand, a smaller and cheaper component like a fastener or a screw is more readily available. In addition, we can segment this availability not only on the basis of stock quantity, but also factor in supply chain interruption by analyzing the likelihood of the suppliers not meeting their obligations. This is where Monte Carlo comes in, since we can even estimate their COVID-related impacts by calculating the resilience of the second and third order supply chains based on, let's say, the size and scale of their business probabilistically. The same reasoning applies to the workforce component of the equation. Some skills are significantly more rare and difficult to replace, for example, a test pilot, while the availability of others can be worked around to an extent. In our experience, COVID impact to the workforce tends to express itself as absenteeism, and therefore decreases the total amount of labor hours that can be effectively deployed at every step of the assembly process. An interesting nuance is that some of the traditional approaches to solving this problem, such as crew rotation, social separation, masks, and increased hiring, can in reality negatively affect other variables. For example, increasing avoidable mistakes and the associated rework hours, especially for new, less experienced staff. Last, we wanted to cover facility space, since in most aircraft production lines, there's quite a bit of work occurring in parallel, with multiple aircraft in the same phase of the assembly at the same time. This can provide another lever for the decision maker when evaluating possible courses of action, since making smart structural changes to the factory floor layout can certainly serve to increase the overall throughput. And so by analyzing legacy data on each of these three factors, we were able to create baselines and then work with the client's internal team to develop some assumptions and projections about future availability of each, given the evolving pandemic. Some of these were probabilistic, and some were informed by subject matter opinion. Putting all of this together, we were able to build a simulation of the entire factory, which contains digital twins of each of the aircraft undergoing assembly activities and projects several scenarios for the best, worst, and expected case outcomes. Let's take a look. This capability to simulate an industrial production line was developed using the AnyLogic modeling platform, which is a low-code COTS, commercial off-the-shelf, tool that's been widely adopted by the ORSA community. At its heart, this is a discrete event plus Monte Carlo engine that allows our manufacturing clients to create digital twins of each of their aircraft assets, monitor them during every step of the build process, and forecast future performance. Let me go ahead and launch the simulation. And the very first thing that I wanted to do is draw your attention to our legend on the bottom left. So it looks like this sample factory is producing a total of 4 different aircraft. And then also, if any of them experience an issue due to a part defect or a delay, we immediately highlight them for the user. Now, moving to the top here, the top ribbon is the logical view of our production line. So we start with the main assembly sequence, then we transport the aircraft, we proceed to flight line testing, and then ultimately delivery. Now notice that each of these main steps has been further broken out into the different workstations. It's important to remember that in each of these areas, different kind of work gets completed. And that requires different number of hours by different specialists or skill types. So when we resource load this with an actual footprint and actual staffing and hours that are being spent on the production line, it gives us a really accurate method for forecasting how long it takes for each of these aircraft to complete every one of these steps. Now, in addition, each workstation consumes a different types of parts from our safety stock based exactly on the type of an aircraft that is being built. So in reality, each of these icons moving from left to right is a representation of the percentage of the work that has been completed on that aircraft at that station. And then, of course, as aircraft complete and they're delivered, we keep track of all of that and we start plotting them on this chart on the bottom left. Let me accelerate time a little and we'll see if we can go ahead and identify an aircraft that runs into a delay. So once we do, we will be able to click on that aircraft and get all kinds of statistics behind the parts that have caused the shortage. So in this case here, I'm going to go and click on him here in electronics. I'm going to reset it to 1x and resume. And so what you'll be able to see in our aircraft log and diagnostics, so this was type 4 aircraft that ran into these 3 part defect and shortage issues. And then we can continue tracking it through the end of its build progress. Now, the very interesting thing to point out is when you look at the chart that's building on the lower right is how accurate the outputs of the simulation are versus historic actuals. So historic actuals I have in green and the simulated results in orange. Now, there's a little bit of a difference between the two, and that's actually healthy because we could have continued to calibrate the simulation until those matched perfectly. But there will always be things that occur in the real life that diverge from the simulation assumptions. And that's okay, because ultimately one of the main measures is area under the curve when you compare the total amount of produced by the simulation versus actuals. And as you can see, those are very close. I mean, there's of course other statistical tests that one would do in order to make sure that we can trust the results. But the key takeaway point here is that, as you can see, we're doing this test using the last 2 years of data. And the conclusion that we came to is that if the simulation is accurate over the course of 2 years in predicting the historic actuals, then we can call it inaccurate enough to allow us to do future predictions, because by running this forward in time and then also modifying some of the assumptions behind evolving conditions on the factory floor, for instance, absenteeism in light of COVID or additional disruptions to the supply chain, we can actually come up with a really precise model that allows us to, in simulation, evaluate all these different scenarios, right? What is going to be the best case? What is going to be the worst case? And then in between them, what is going to be the average or expected case? In short, we use this to predict future volumes. So build times, anticipated production dates by each individual aircraft, plus aggregate totals. We also use it to evaluate the build process itself and help us identify constraining steps. Finally, we use it to test scenarios, ranging from COVID-related absenteeism and reduction in workforce efficiency to COVID-related interruptions of the underlying supply chain. And most importantly, we use it to help our clients evaluate what-if alternatives and various potential corrective actions that they can take, first in simulation and then on production floor. We really appreciate this opportunity today to share with you some of our thinking, lessons learned, common definitions, techniques, and outcomes of simulation and digital twin projects. We hope that this brief introduction was as interesting as it was informative, and like all good conversations, created more questions than it answered. I wanted to leave you with one of my favorite quotes by the late George Box. He said, "All models are wrong, but some are useful." I hope you take that to heart as you think through the potential applications of simulations to your problem. The real art, and honestly the tricky part of this entire discipline, is in making this decision on the correct level of abstraction. All things being equal, don't paint a Mona Lisa when a simple smiley face will do, as long as the outcome of the model can be accurate enough to support a decision. Thank you for your time.